Grab your calipers and your sense of humor because we're about to measure how much bullshit the textbooks left out. This is mechanical engineering made simple.
Oh, I love that intro. It's very fitting for what we're doing today.
Thanks. Welcome to the deep dive, everyone. Today, this deep dive is entirely for you. And, I mean that quite literally. We know you're the type of person who wants the actual knowledge, but you want the real story.
Right, the actual substance.
Exactly, the aha moments, but without feeling like you are just, drowning in a sea of academic jargon or staring cross-eyed at a chalkboard. So we are taking a dense, advanced dynamics textbook specifically, this wildly complex chapter on the dynamics of a system of particles.
It is a heavy one.
It really is. And we are stripping away that dry, sterile veneer to reveal the wild, high-stakes reality of physics.
Yeah, it's quite the journey we have mapped out for this one. When I first looked at this source material, the mental image I got wasn't a dusty lecture hall at all.
Was it?
I pictured glowing three-dimensional planetary grids. I saw complex missile flight paths carving through the stratosphere and high-speed, incredibly visceral crash test footage.
Oh, wow.
Because honestly, beneath all the Greek letters and the calculus, that is what this math actually describes. It is the physics of survival. It's about how things move, how they break, and how we, predict the unpredictable.
I love that, the physics of survival. And that's our roadmap for today. We're going to figure out how engineers basically cheat reality to simplify the absolute chaos of spinning objects.
They absolutely do cheat.
Great. And then we are going to look at a scenario where a multi-million-dollar missile defense system completely misses its target simply because someone assumed the Earth was flat for just a 2-hour drive.
That part is fascinating.
And finally, we will break down the brutal, unforgiving physics of real-world car crashes. So let's get right into the first major concept from the text.
Let's do it.
The sources spend a lot of time establishing how we look at systems of particles, which honestly, it sounds a bit like an illusion to me. It's like they're trying to hide all the messy details.
Yeah, the illusion of the point. That's a very good way to frame it, actually. To understand how engineers tackle real-world problems, we have to look at how the textbook starts.
Mm-hmm.
It introduces this concept of a system of n particles.
Okay, let's unpack this. What is n?
Well, in mathematics, n just means an arbitrary number.
Right.
It could be a dozen, a million, a billion, or, a trillion. Now, imagine any solid object. A baseball, a wrench, a car. It is not just one thing. It is made of countless atoms and molecules, and every single one of them is interacting.
Right. I mean, they aren't just sitting there peacefully. They are vibrating, they are pulling on each other, they are bound by these microscopic atomic forces.
Exactly. They are an absolute swarm of chaotic activity. And every single one of those particles is subjected to two broad categories of forces. First, you have your external forces. This is easy to visualize. It's gravity pulling down on the baseball, or the wind resistance pushing against the windshield of a car.
That makes sense.
But then you have the internal forces.
Which would be like the interactions between the particles themselves, the glue holding the thing together.
Yes. And this is where the math should, theoretically, become completely impossible.
Why is that?
Think about it. If you tried to calculate the trajectory of a thrown wrench by tracking the individual motion, the gravitational pull, and the electromagnetic interaction of every single atom inside that wrench,
Oh, man.
you would break a supercomputer. It is a mathematical nightmare of infinite complexity. You just cannot track a billion variables simultaneously to figure out where a wrench is going to land on the floor.
So how do engineers actually get anything done? Because if I throw a wrench, I can pretty easily predict where it's going to hit. The math must have some kind of backdoor. Yeah.
It does. It has a huge one. And the textbook offers us this massive, universe-altering shortcut, courtesy of Sir Isaac Newton. It all comes down to Newton's third law of motion.
For every action, there is an equal and opposite reaction. I think we all had that drilled into our heads in grade school. But how does that save us from the math nightmare?
Well, think about what that law actually implies for those internal forces we just talked about.
Okay.
The text explicitly states that the internal forces, the microscopic pushing and pulling these particles exert on each other, they all obey Newton's third law.
Right.
Therefore, if atom A pulls on atom B with a certain microscopic force, atom B is pulling back on atom A with the exact same amount of force, just in totally opposite direction.
Okay, I see where this is going. If you zoom out and look at the whole wrench.
Exactly. When you sum them all up, they perfectly cancel each other out.
Yeah.
Every single internal force has an exact twin pointing the opposite way.
That's wild.
So when you add up all the internal chaotic pushing and pulling across the entire system, the sum is exactly 0.
Wow. Okay, it's like imagine watching a chaotic flock of birds.
Oh, I like
The
that.
birds are darting around each other, diving and weaving. Those are like the internal forces canceling out, but the flock itself is moving steadily across the sky. Engineers don't track every bird, they just measure the center of the flock.
That is a phenomenal analogy, yes.
Yeah.
The internal darting doesn't change the trajectory of the whole flock moving south for the winter. That center of the flock is exactly what the textbook calls the center of mass.
The center of mass. Got it.
By mathematically summing up all the individual masses in their specific locations, engineers find a single theoretical point. And then they can treat millions of chaotic particles as if they were just one single, infinitely dense point mass, located perfectly at that center.
That is just wild to think about. I mean, for you listening, whenever you see a textbook or an engineering diagram showing a massive rocket or a whole planet as just a single tiny dot on an XY graph, that dot isn't just a lazy drawing. It's a mathematical certainty. The laws of physics are literally handing engineers a permission slip to ignore the infinite complexities of an object's internal structure just so they can plot its general movement across space.
It is the ultimate simplification. But, the textbook doesn't stop there.
Of course not.
Because once it establishes that we can treat a complex object as a single point moving through space, it has to address reality. Real objects don't just slide perfectly from point A to point B without any other movement. They tumble. They spin.
Right, like we said, if you throw a wrench, it spins end over end while it flies through the air, or the Earth spins on its axis while it orbits the sun.
Exactly. And this is where the textbook transitions into explaining angular momentum.
Okay.
Angular momentum is just the measure of how much rotational motion an object has. And the math here is actually quite beautiful in how it compartmentalizes the problem.
Klaus.
Well, the text explains that the total angular momentum of a system, let's just stick with our tumbling wrench for a second, is actually the sum of two entirely distinct calculations.
Okay, lay them out for me.
First, you calculate the angular momentum of the entire mass of the wrench as if it were crammed into that single center of mass point we just talked about, moving through space relative to wherever you are observing it from.
So if I'm standing across the room, that's just tracking the physical movement of that center dot traveling through the air toward me.
Correct. That's the translation, the physical movement of the object from one coordinate to another coordinate. But then you add the second part,
Which is?
the angular momentum of the system spinning around its own center of mass.
Ah, okay. So you separate the journey from the spin.
Yes, exactly.
You track the center dot flying across the room, and then you just attach a totally separate math equation to that dot that basically says, by the way, this dot is spinning at 300 RPM.
Yes. You completely isolate the translation from the rotation. The textbook highlights this as absolutely crucial for studying the rotational motion of solid bodies.
Because doing it all together would be impossible.
If you tried to calculate the flight path of just the handle of the wrench, the math would be this swirling, looping, unreadable nightmare. But by tracking the center of mass, the flight path becomes a clean, elegant parabola, and the rotation is just a separate property sitting on top of that point.
So we have this perfect mathematical illusion. We take a chaotic, spinning, complex object, and we shrink it down to a single obedient point on a graph.
Yep.
It's clean, it's neat. But I have a feeling that this textbook is about to pull the rug out from under us.
It definitely is.
Because simplifying one object is great, but what happens when you have to deal with the vast space between objects?
That is exactly where the source material takes a very dramatic turn. Treating a single object as a point is a brilliant shortcut.
Yeah.
But things get incredibly profoundly complicated when you have two distinct points moving across a massive expanse of space. And that brings us to section 3.2 of the textbook. This isn't just theory anymore. This is the ultimate high-stakes physics problem.
We are talking about hitting a bullet with a bullet, the mid-air collision of two missiles.
Yes. The textbook sets up a very detailed, very specific scenario to explain coordinate conversion and trajectory. Let's paint the picture for you.
Oh.
Imagine you are in a defense command center.
Okay, I'm there.
An enemy missile has been launched from a hostile site. We'll call this the target missile. It's detected by a satellite system.
Yeah.
Based on the telemetry, we know its net thrust is a constant 14,500 newtons.
And to stop it, we have to launch our own missile, an interceptor. But in the real world, things take time.
They do.
It took time for the satellite to see the launch, time for the computers to crunch the trajectory, time to authorize the countermeasure. So our launch is delayed by 60 seconds.
That is a massive disadvantage. We're a full minute behind.
Yeah, that's an eternity in missile flight time.
Now, our Interceptor missile has an initial mass of 1,000 kilograms. It has a stronger engine, pushing a thrust of 16,000 newtons, and it launches with an initial velocity of 300 meters per second.
Okay, but wait, a rocket doesn't just stay at 1,000 kilograms, right? If you've ever watched a space launch, you know most of a rocket is just fuel that it burns violently to get off the ground.
Exactly, and the textbook actually models this reality. To generate that 16,000 newtons of thrust, our Interceptor is continuously burning fuel and ejecting mass out of the exhaust nozzle. The text specifies a mass decreasing rate of 3 kilograms per second.
Oh, wow. So every single second it's in the air, the missile becomes 3 kilos lighter.
Which means its acceleration is constantly changing. Think about it. The engine is pushing with the exact same constant force, but the object it's pushing is getting lighter and lighter every single second. So the missile accelerates faster and faster as it flies.
That totally makes sense. It's like if you were pushing a shopping cart full of bowling balls with a steady force and someone was just chucking the bowling balls out one by one.
Great visual.
The cart would speed up even if you didn't push any harder. So the math is already a headache. You have constantly changing mass, nonlinear acceleration, different launch times. But here is the variable that really caught my eye in the source material.
Which one?
The textbook places these two missile launching sites 200 kilometers apart.
Yes. 200 kilometers. That is the critical variable.
Okay, here's where it gets really interesting, and I have to push back on this. Because 200 kilometers is basically just a 2-hour drive. It's like going from Los Angeles to San Diego.
Right.
In the grand scheme of the planet Earth, which is massive, a 2-hour drive down the highway is nothing. Does the curve of the Earth actually matter on a scale that small? I mean, surely you could just treat the ground between the two launch pads as perfectly flat, right?
That is the exact trap the textbook wants to see if you fall into.
Yeah.
It explicitly asks, what happens if we treat the Earth as flat ground for this scenario?
Really? They test you on it.
They literally provide the Fortran computer code in the text to run this exact simulation. They use a trial and error method to find the exact launch angle needed for our interceptor to hit the target.
All right, so on our theoretical flat Earth, what is the magic launch angle?
Assuming the ground between the two sites is a perfectly straight horizontal line, the computer model dictates that our interceptor missile requires a launch angle of exactly 0.9821454 radians.
0.9821454 radians. Okay, I need to translate that for my own sanity. A radian is just another way to measure an angle, like degrees. 1 radian is roughly 57 degrees, so 0.98 radians is somewhere around, what, 56 degrees off the ground?
Yes, roughly 56.27 degrees.
Yeah.
You've programmed that exact angle into the launch computer. The flat Earth math says the missiles will collide beautifully in the sky at exactly 144.8 seconds after the enemy missile launch.
Perfect.
The simulation shows the distance between them dropping to less than 8 centimeters, which is well within the explosive radius. It defines this as a totally successful intercept.
So the flat Earth math works perfectly. We saved the day.
We save the day in a universe where the Earth is a flat plane, but we don't live in that universe. And this is where the textbook delivers the brutal reality of planetary geometry.
The spherical ground model.
Exactly. When you have two coordinate systems, our launch pad and the enemy's launch pad, separated by 200 kilometers on the surface of the Earth, the text explicitly warns that the effect of the spherical surface must be taken into consideration.
I still can't wrap my head around the fact that 200 kilometers makes a tangible difference. It just feels too close.
It is super counterintuitive, but let's break down the physical reality. The Earth has an average radius, which the text denotes as R0, of 6,371.23 kilometers.
Okay.
Imagine standing on a perfectly smooth Earth. If you shoot a laser pointer perfectly straight out, perfectly horizontal to your eye level, that laser beam travels in a perfectly straight line. But the Earth is a sphere. As the laser travels 200 kilometers away, the ground physically curves downwards and drops away from that straight line.
Oh, wow. Okay,
Yeah.
so the straight line goes out into space, but the ground is actually sinking underneath it.
Precisely. The text provides the exact formula for this coordinate conversion. Your z-axis, which is your vertical height, isn't a simple straight grid line anymore. You have to account for how much the ground has dropped.
How do they calculate that?
The new vertical coordinate uses an equation that subtracts the Earth's radius multiplied by the cosine of the angle between the two cities from the center of the Earth.
I definitely don't want to get bogged down in the cosine math, but conceptually, what you're saying is that because the Earth is curved, the enemy's launch pad is physically lower down in space than it would be if we were on a flat plane.
Yes. If you draw a straight, level line from our launch pad, the enemy launch pad 200 kilometers away is physically sitting below that line, literally obscured by the curvature of the Earth.
That is so crazy to think about.
And because they are on a curve, the straight line horizontal distance through the crust is slightly different than the surface distance, too. When you feed these actual spherical coordinates back into the computer program, the entire geometry of the intercept shifts.
Okay, so the flat Earth angle was roughly 56.27 degrees. What is the new magic angle? What angle do we actually need to launch our interceptor at on a real spherical Earth?
On the spherical surface, to achieve a successful collision, the interceptor missile must actually be launched at 0.9929676 radians.
4.9929676 radians, which is roughly, let me think, 56.89 degrees. Wait.
Yeah.
The flat ground angle was 56.27 degrees. The spherical angle is 56.89 degrees. That is a difference of roughly 0.6 degrees. That is a microscopic fraction of a shift at the launch pad. It's barely a nudge of the launch tube.
It is a tiny adjustment. But think about how trajectories work. A tiny fraction of a degree at the starting line becomes a massive divergence miles up in the stratosphere.
Oh, I see.
And this raises the ultimate question, which is the exact warning the textbook issues to the engineering student reading it. What happens if you get lazy? What happens if you assume 200 kilometers is small enough to just use the flat Earth calculation?
Okay, I'm holding my breath. What happens?
The textbook states the result unequivocally. If the launch angle is set according to the flat ground formulation, if you use the 56.27 degree angle on our actual spherical Earth, the second missile will not collide with the target.
It just misses.
It misses entirely. The computer simulation terminates because it sees the distance between the two missiles reaching a minimum, but not a collision, and then that distance just starts increasing again. They fly right past each other.
That is absolutely terrifying.
It is the ultimate so what of this entire source material. A textbook simplification, ignoring the curvature of the Earth for a distance equivalent to a morning commute between cities, literally results in a catastrophic mission failure.
Wow.
The enemy missile gets through, and a city is destroyed, all because your math was too simple. It proves that you cannot ignore the physical, geometric reality of the planet, no matter how convenient or easy the math might be.
So we've learned two completely opposing lessons here, which is fascinating.
What do you mean?
Well, in the first scenario, engineers use the center of mass as a shortcut. The laws of physics give you a permission slip to simplify a complex, chaotic object into a single point.
Right.
But in this missile scenario, the physics strictly forbid you from simplifying the space that the object travels through. You can shrink a rocket to a dot, but you cannot flatten the Earth.
That is a brilliant synthesis. The geometry of space is unforgiving. You absolutely must respect the curvature.
Wow. Okay, so we've successfully hit a bullet with a bullet in the high atmosphere, but missiles are, by their very nature, designed to explode upon intercept. They are meant to destroy each other.
Yes, they are.
What happens when everyday objects collide on a smaller terrestrial scale? I want to bring this down to the pavement. The textbook shifts gears here to talk about what it calls the physics of the smash.
It does. It moves from the macro scale of planetary trajectories down to the micro scale of impact mechanics. And the text defines impact very precisely. It's not just two things touching.
What is it then?
An impact is the action of two bodies colliding with a massive inertial force in an incredibly short time interval.
A huge amount of force crammed into a tiny fraction of a second. A crash.
Exactly. And before it gets into the destruction, the sources break down the geometry of how things hit. You have two objects, and the text models them as spheres just to keep the geometry clean.
Right.
If they hit dead straight on, where their centers of mass are perfectly aligned with their velocities, that is called a central impact.
Okay, so imagine two bowling balls rolling down a perfectly straight lane and hitting exactly dead center.
Correct. But if their velocities are angled away from that direct center line, it is an oblique central impact.
Think of a glancing blow, like a car drifting into the side of another car, sending them both spinning on in different angled directions.
Exactly. So the geometry tells us how they hit. But geometry doesn't tell us what happens to the objects themselves. When two things smash together, the outcome really depends on what they are made of.
Right. Two glass ornaments crashing together is a very different outcome than two rubber tires crashing together.
And that is exactly where the textbook draws a massive line in the sand. It categorizes all impacts into two fundamental types of collisions based on material properties: elastic and inelastic.
Let's start with elastic. Now, the classic high school physics example is always billiard balls on a frictionless table, but let's be real, that's a pretty tired cliche.
It is a bit overused.
Give me a better visual for an elastic collision.
Fair enough. Imagine you're standing inside a bank vault with solid steel walls, and you throw a perfectly made, high-density super ball as hard as you can against the wall.
Okay, I'm throwing it.
In an elastic collision, the impulsive force, the violence of the smash, is not severe enough to push the materials past their yielding points.
The yielding point, that's the threshold where a material stops bending and starts permanently breaking or deforming, right?
Exactly. Every material has a limit. In our vault, during the split second of impact, the super ball flattens out against the steel wall. It compresses like a tightly coiled spring. But because it hasn't passed its yielding point, the moment the energy transfer peaks, it restores completely to its original spherical form.
It snaps back.
It snaps back perfectly. There is no permanent deformation.
It doesn't leave a dent in the wall, and the ball isn't squashed flat.
Precisely. And mathematically, this is a physicist's absolute dream scenario. Because nothing was permanently broken or bent, the textbook states that the kinetic energy of the system is entirely conserved.
So it's like a perfect energy bank account. All the energy of motion you spent throwing the ball into the wall is perfectly refunded back into the ball as it bounces off.
Yes, exactly. The total momentum is conserved, and the total kinetic energy is conserved. If you know the mass of the ball and how fast you threw it, you can calculate the exact velocity it will bounce back with absolute certainty. The math is clean, it's balanced, it's beautiful.
But the real world is almost never that clean. I mean, things break, bones break, metal twists. What about when we push past that yielding point?
That brings us to inelastic collisions. This is where the stresses produced by the impact force absolutely overwhelm the yielding strength of the materials involved.
So instead of throwing a super ball at the vault wall, you throw a ripe tomato, or on a larger scale, a sedan wrapping around a concrete pillar.
Exactly. In an inelastic collision, the material fails. Permanent deformation results. The tomato bursts, the metal of the car crumples, the glass shatters, the frame twists.
It's just destruction.
And here is the critical physics reality. When you permanently deform a material, energy is dissipated. It is consumed.
Wait, where does it go? Energy can't just disappear, can it?
No, it doesn't disappear. The textbook calls it stress-strain energy. The kinetic energy, the sheer speed and mass of the moving car, is literally converted into the physical work of ripping atomic bonds apart, generating heat, and permanently bending steel.
Wow, so the perfect energy bank account is gone. The conservation of kinetic energy goes entirely out the window.
Completely out the window. And this creates a huge problem for engineers trying to predict a crash.
Yeah.
They can't just balance the energy equation anymore because they don't know exactly how much energy the crumpled metal just ate.
Right, because every crash is different.
Exactly. They need a new variable. They need a way to quantify exactly how much energy is lost to the destruction of the material versus how much is left over to bounce the objects apart.
And what does the textbook give us to solve that?
It introduces a brilliant little variable called the coefficient of restitution, and it's denoted in the math by the lowercase letter e.
The coefficient of restitution, okay, I need to visualize this. What exactly is he measuring?
Well, the textbook defines it formally as the ratio of the impulse during the restitution period to the impulse during the deformation period.
Whoa, okay, hold on. Impulse, restitution, deformation. That's a lot of textbook jargon. Walk me through the timeline of a crash, like millisecond by millisecond.
Okay, let's slow it right down. Imagine two cars colliding head-on, captured on an ultra-high-speed camera. The exact millisecond their bumpers touch, the deformation period begins.
The crunch.
Right. The force skyrockets. The bumpers shatter, the hoods fold like accordions, the engine blocks smash into each other. The materials are compressing and squashing.
Okay, I see it.
But as they squash, they're slowing each other down. Eventually, they reach the point of maximum compression. At that exact singular split second, the crushing stops. And for just a fraction of a millisecond, both cars are moving at the exact same velocity along the line of impact.
Like they're fused together.
They are essentially one single mangled mass of metal.
Okay, so deformation is the energy going into the crash.
Yes. Now, immediately after that maximum compression, the restitution period begins. This is the attempt by whatever is light of the structural integrity to push back. It's the interval between maximum compression and the moment the objects finally push apart and separate.
So restitution is the bounce back? So if I'm understanding this, it sounds like the math of a car crash is entirely dictated by how much bounce a material refuses to give back.
That is a beautiful way to summarize it. The coefficient E is literally a grade on a test of how well an object bounces back. If we go back to our Super Bowl hitting the steel wall, a perfectly elastic crash where all the energy is returned into the bounce, that impact has an E of exactly 1.
A perfect 100% score.
Yes, but real life isn't a Super Bowl.
Definitely not.
No. On the total opposite end of the spectrum, you have a perfectly plastic crash. This is an impact where the objects crunch, stick together, and do not bounce apart even a single millimeter.
Like throwing a giant lump of wet clay against a blight wall, it just splats, deforms, and stops completely.
Exactly. A plastic crash has an E of 0. 0 restitution. 0 bounce. In real-world inelastic collisions like car crashes, ease is always some decimal between 0 and 1 because the impulse is severely diminished during restitution. The metal simply fails to resume its original shape.
Now, connecting this to the real world, this exact concept, the loss of energy to permanent deformation, it has to be the entire mathematical foundation for modern car safety, right?
Oh, absolutely.
Because if I'm in a car crash, I want an inelastic collision. I want the hood of my car to act like wet clay. I want that kinetic energy to be dissipated by the crumpling metal rather than being perfectly conserved and transfers directly into my rib cage.
You've hit the nail on the head. That is exactly why cars are designed with crumple zones. They are deliberately engineered to lower the coefficient of restitution, to force the kinetic energy to be spent destroying the front of the car so it doesn't destroy the passenger cabin.
That's amazing.
And the textbook anticipates this exact line of thinking. It takes all of this collision physics, the momentum, the impulse, the deformation, and applies it directly to the most common high-stakes physics experiment in the modern world, the automobile accident.
Which brings us to the ultimate showdown, the heavyweights of the highway. The textbook literally poses practical, life-or-death questions about highway collisions.
It does.
These aren't just abstract theories anymore. This is about who walks away from a wreck and who doesn't.
The authors note that car crashes are incredibly common occurrences, resulting in hundreds of injuries and deaths daily. They use the physics we just discussed to answer two very specific questions.
Okay, what's the first one?
The first one is a classic. In a collision, is the driver of a heavier car actually safer than the driver of a lighter car?
Now, I feel like everyone instinctively knows the answer to this. If I have to choose between sitting in a massive 3-ton SUV or a tiny, lightweight smart car during a head-on collision, I'm taking the SUV every single time.
Naturally.
It just feels like common sense. But how does the textbook prove it mathematically without just saying bigger is better?
It proves it by relying on the cosmic accounting book we talked about earlier, the conservation of momentum. Let us look at this scenario in example 3.5. We have two-car head-on collision. We will call the lightweight car mass 1 and the heavy SUV mass 2.
So mass 2 is significantly greater than mass 1.
Yes. Two very different weights heading straight for each other. Now, during the millisecond of the crash, we isolate the two cars as a closed system. The external forces, like friction with the road, are completely negligible compared to the massive internal forces they are exerting on each other.
Okay, that makes sense.
Because momentum must be conserved in this system, the total change in momentum for car 1 must perfectly equal the total change in momentum for car 2.
Okay, let me visualize the accounting book here. The momentum a car experiences is its mass multiplied by its change in velocity, right?
Exactly.
So the mass of the tiny car times its massive change in speed must perfectly equal the mass of the huge SUV times its change in speed.
Yes. Now look at the reality of those numbers. Because the SUV has a massive weight advantage, its mass is huge. In order to keep the equation perfectly balanced, its change in velocity has to be relatively small.
Ah, I get it. It's like a seesaw. If you have a really big kid on one side, they don't have to move very far up or down to balance out a tiny kid flying high up into the air on the other side.
That's a perfect analogy. The heavy SUV basically bullies the tiny car. The heavier car undergoes a much smaller change in velocity during the impact. The tiny car is forced to absorb a massive, catastrophic change in velocity.
Okay, but how does that translate to the human being sitting in the driver's seat? The car's velocity changes, but the driver isn't welded to the frame. They have a seatbelt, sure, But their internal organs, their brain inside their skull, those things still have to absorb the shock of stopping?
The textbook brings the math directly to the human body by calculating what is called the inertial force.
Inertial force.
Let us assume the drivers in both cars are identical. They both weigh exactly the same. The inertial force acting on a driver's body, the invisible hand that throws you forward against the seatbelt, is equal to the mass of the driver, multiplied by the car's change in velocity, divided by the time interval of the crash.
Okay, let's break that down. The mass of the driver is the same in both cars. The time interval of the crash, the fraction of a second it takes to crunch the metal, is exactly the same for both drivers because they are crashing into each other at the exact same moment.
Which leaves only one single variable determining how much force crushes the driver's chest. The change in velocity.
And because the massive SUV experienced a much smaller change in velocity, the human inside the SUV experiences significantly less sheer inertial force on their body.
Mathematically, yes. The inertial force tearing at the organs of the driver in the heavy car is demonstrably, provably less than the force on the driver in the lightweight car. The heavy car acts as a sheer mass advantage shock absorber.
Wow.
The heavier car always wins. The textbook concludes, plainly and brutally, that the injury to the driver in a heavier car will be less than the injury to the driver in the lighter car.
It's just undeniable, unforgiving physics. Mass protects you.
Yeah, it does.
But what about the driver's actions before the crash? Because this brings up the second question from the text, and I'm so glad it's in here. I have heard this argued in bars, in living rooms, and by older relatives my entire life.
Ah, yes. I know where you're going. The urban myth of the accelerator.
Yes. The myth goes like this. If you are driving and you realize you are about to crash head-on into someone and it is totally unavoidable, you shouldn't slam on the brakes. You should actually hit the gas.
People really believe that.
They do. The logic is that by accelerating into the crash, you give your car the momentum advantage, forcing the other car to take the brunt of the impact. Does the math actually back up this barroom wisdom?
The textbook dedicates example 3.6 to utterly dismantling this myth. It sets up a scenario to mathematically estimate the difference in impact force between braking, coasting, and actively hitting the gas.
Okay, let's hear the numbers.
Set the baseline first. We have two identical cars heading straight for each other.
Identical cars this time, so no mass advantage. What are the specs?
The textbook uses the imperial system for this engineering example. The mass of both cars is stated as 100 slugs.
Okay, pause. 100 slugs. I know we're using imperial, but what on earth is a slug? I've bought a lot of cars, and I've never seen the weight listed in slugs.
It is a wonderfully esoteric unit of mass used by engineers, because pounds actually measures force, specifically the force of gravity pulling on an object. Engineers needed a separate unit for pure mass.
Okay.
One slug is defined as the mass that accelerates by 1 foot per second squared when 1 pound of force is applied to it.
That sounds complicated.
It's not too bad. Because Earth's gravity accelerates things at about 32.2 feet per second squared, one slug is roughly equal to 32.2 pounds of mass.
Okay, so a 100 slug car is just 100 times 32.2. It's a 3,220-pound car.
Exactly.
That's just a standard mid-size four-door sedan.
Correct. Two standard sedans. They're both traveling at a constant velocity of 50 miles per hour. They hit dead center, head on. And the text defines the duration of the impact, that critical time interval of the crunch we talked about, as 0.020 seconds.
200ths of a second. That is unimaginably fast.
It is incredibly violent. In 200ths of a second, both cars are completely stopped, crumpled together. To find the baseline impact force, we first have to convert that 50 miles per hour into feet per second to match our slugs.
Right.
The text does the conversion, giving us a change of velocity of 73.5 feet per second.
Because they go from moving at 73.5 feet per second instantly to zero in 0.02 seconds.
Correct. So to find the baseline force of the crash, we take the mass 100 slugs multiplied by the change in velocity 73.5 and divide it by the time 0.02.
Okay, I want everyone listening to picture this. Two normal sedans driving a normal highway speed of 50 miles per hour hitting head-on. What is the actual force of that crash?
It generates a devastating impact force of 367,500 pounds of force.
367,500 pounds of force. That is over 180 tons of crushing force localized on the front of that sedan happening in 200ths of a second. That is horrifying.
Yes. That is the baseline reality of highway physics. Now, the textbook runs the second scenario to test the myth.
The hit the gas myth.
Exactly. What if one of those drivers, moments before the impact, panics or tries to be a hero and slams on the gas pedal? The text assumes they managed to accelerate their car at a rate of 5 feet per second squared right before impact.
Okay, so they are actively driving into the crash. They've got the engine roaring, the tires pushing against the pavement. They have the momentum advantage, right? What happens to the math?
When a car accelerates, it applies a force to the ground through the friction of the tires, which pushes the car forward. So to calculate the new total impact force, you take the baseline crash force we just calculated and you add the extra external force generated by the car's acceleration.
Okay, so we take that massive 367,500 pounds of force and we add how much force does slamming the gas pedal actually generate?
Force equals mass times acceleration. We take the mass of the car, 100 slugs, and multiply it by the acceleration of 5 feet per second squared. The added force from hitting the gas is exactly 500 pounds of force.
Wait, just 500 pounds?
Yes. So the total impact force of the crash rises from 367,500 pounds to 368,000 pounds of force.
That's nothing. It's a rounding error.
It is a microscopic rounding error against the massive, overwhelming kinetic energy of the crash. The textbook puts it very dryly. It says, the result shows that the impact force due to the acceleration of one car is very small compared with the total impact force.
It is basically a 0.1% difference. Hitting the gas does absolutely nothing to give you a momentum advantage. All it literally does is add slightly more speed and slightly more total energy to an equation that is already completely lethal.
Exactly.
You aren't powering through the other car, you are just ensuring that you hit a solid brick wall slightly harder than you would have otherwise.
That's it. The human intuition fails here because we just don't naturally comprehend kinetic energy at high speeds.
Yeah.
The energy of 3,200-pound objects moving at 50 miles per hour is so astronomically high that the paltry, pathetic force your little combustion engine can generate in a fraction of a second is completely irrelevant to the physics of the smash.
Your engine simply cannot output enough mechanical force to alter the math of a 180-ton impact.
Yeah. Precisely. The myth is definitively mathematically busted. Hitting the gas is the worst thing you can possibly do.
That is just incredible. The numbers simply do not lie. So, to recap this incredible journey we've been on today, we started by looking at the illusion of the point, how engineers use Newton's third law to cancel out internal chaos, allowing us to simplify massively complex, spinning objects into neat, obedient single dots on a graph.
It is a vital, brilliant shortcut for understanding rotational dynamics and keeping the math of angular momentum manageable.
Right. But then we saw the strict limits of that simplification. We learned why flat Earth math completely fails missile defense systems at a distance of just 200 kilometers.
Yeah, that 0.6-degree difference.
We saw how the subtle physical curve of the planet literally drops a target completely out of the way of a perfectly calculated straight-line interceptor.
Proving that while the physics allow you to simplify the object itself, you can never ignore the true geometry of the space it travels through.
And finally, we brought it all down to the pavement with the brutal reality of car crashes. We saw how inelastic collisions rob a system of kinetic energy through the permanent, violent deformation of metal.
The stress-strain energy.
Yeah. We saw the math behind why heavy SUVs act as shock absorbers, protecting their drivers by forcing the lighter car to absorb the massive velocity change. And we finally put a stake through the heart of the hit the gas myth, proving that accelerating into a crash is a fool's errand that only adds 500 pounds of force to a 367,000-pound catastrophe.
Hopefully, understanding these concepts gives everyone listening the mathematical tools to look at the physical world around them and the textbooks that attempt to describe it with a far more critical and informed eye.
It really changes how you look at a highway, that's for sure.
Yeah.
But before we let you go, our expert found one final mind-bending concept buried in the source material that we haven't touched on yet, and it is going to stick with you long after you take your headphones off.
Yes. In section 3.4, the textbook takes a slight detour to discuss gravitational force and potential energy. We talked earlier about gravity pulling our missiles down, and in all those calculations, the math treats the Earth like a massive point mass, with all of its infinite gravity concentrated directly at its core.
Right, because of that center of mass rule we learned right at the beginning, it makes the math easy if we just pretend the Earth is a dot pulling us down.
Exactly. If you are standing on the surface or flying in the stratosphere, the Earth acts perfectly like a single point of gravity pulling you toward its center.
Mm-hmm.
But the textbook sets up a very strange thought experiment.
I love thought experiments.
What happens if you aren't on the surface? What happens if you are inside the Earth?
Inside it, like deep in a mine shaft.
Deeper. Let us assume you could drill a perfectly clean, frictionless hole straight down past the crust, past the mantle, and you simply jump in and fall inside a solid, uniform sphere like the Earth.
I don't hear it falling.
The textbook actually provides the calculus for this scenario. It calculates the gravitational pull by integrating all the microscopic pulls of all the infinitesimal volume rings of Earth surrounding you as you fall.
Okay, so you jump in, you are falling toward the center, gravity is pulling you down, making you fall faster and faster.
Initially, yes. But think about what happens as you fall deeper. There is now thousands of miles of rock and mass above your head.
Oh, true.
And mass exerts gravity. So that rock above you is pulling you up. The deeper you go, the more mass is physically above you, pulling upwards, actively canceling out the gravitational pull from the mass that is still below you.
Wait, so gravity is fighting itself?
Exactly. The math in the textbook proves that the gravitational intensity, which we denote as g, is directly proportional to your distance from the center. As your distance from the center shrinks and approaches zero, g also approaches zero.
So as you reach the exact dead center core of the planet.
The gravitational force is absolute zero. The surrounding mass of the entire planet is perfectly distributed all around you, and it perfectly cancels itself out in every direction. If you reach the core, you wouldn't be crushed by gravity. You would experience no gravitational pull whatsoever.
Just imagine that for a second. We spend our whole lives on the surface surviving all these brutal, high-speed collisions, calculating the terrifying trajectories of missiles over curved ground, relying on the crumple zones of our cars to save us from the crushing weight of impact forces.
That's a lot.
We live in a violent, high-gravity world, and yet, if you could just survive the fall and make it to the very core of this chaotic, massive planet, you would just float, completely weightless, hovering in perfect balance at the absolute center of the Earth. Grab your calipers, folks. The physics are wild.